Okay, hi there. Welcome to the first video on mechanics year 13, and this is chapter 6, which is called Projectiles. Okay, so first thing to say to you is you can see sort of up here on the board the two main ideas. This is a shorter chapter, and the two main ideas are, first of all, that we are projecting. So projecting, it's just worth saying, projecting, you want to think of projecting as being like throwing. Okay, so why am I saying this? I'm saying this because when something's projected, there's a force right at the start that makes something happen, but then a force is no longer applied. Okay, it's in the air, it's in free fall, so g is the acceleration value, for example, that we would use with a suvat. Vertically. So it's worth saying this because you've done lots of work recently on forces being constantly applied to objects, but projected means they've been thrown. Okay, so here's an example of what it might look like. So we start with things going exactly horizontal, and this is a relatively easy situation to deal with, you're going to see. But then we'll move on to talking about projecting at an angle. So this is a bit like that year 12 chapter for suvat, but the idea is that we're going to work vertically and we're going to work horizontally, and we're often going to kind of use these results together, even though they are very, very separate. Okay, so key theme of this is that vertical and horizontal, they have their own sort of sets of numbers and they work independently to one another. Okay, so let's sort of start with a question then. So a particle is projected horizontally at 25 meters a second from this point here above the ground. Okay, so we're trying to do some things. So I'm going to show you a bit of general advice for how I go about this. So the way I tend to do these questions is I tend to separate my horizontal and my vertical numbers. So horizontally, what I'm going to do is I'm going to say I'm looking at distance, speed, and time. Now, you don't have to do it this way. I'm doing it this way because the key assumption that we make horizontally is that horizontally there is no acceleration. Okay, so that means, for example, that there's no sort of resistance horizontally, and that means that the U, the initial, is equal to the V. So that's why I've just written S for speed and I haven't got an A figure. So different people do it different ways. This is just how I tend to do it. So I'm going to talk about my distance, speed, and time purely, okay, purely horizontally. Vertically, I'm going to write suvat again, and the reason for that is because vertically there is acceleration. In fact, there is constant acceleration, and that constant acceleration is given by g. Okay, so that's why I've got u and v, because they are going to be different values, and that's why I've got a, because there is an acceleration. So this is the start of almost every question I do for projectiles. You're going to see me do this. Let's put some numbers on. So horizontally, it's going 25. And that is only horizontally, if you look here. So it's 25 horizontally, I don't need to do anything with that. Now vertically, what's the initial velocity vertically? It's actually 0. Okay, this is a difficult idea at the start, but horizontal and vertical motion, because they're perpendicular to one another, they are completely separate. Okay, an illustration I would give you for this, which is always a little bit sort of mind-blowing at the start, is if you held a bullet in your hand versus if you sort of fired a bullet from a gun. Okay, unless the bullet's a ridiculous speed, which we're going to say it's not, they would actually both hit the ground at the same time. Horizontally, there's a big difference, isn't there? This one doesn't go anywhere left and right. This one goes very, very far. But the time to hitting the ground, this is the kind of thing that comes from the vertical motion. So because something's going horizontally, that's completely separate to vertically. And this sort of implies that vertically nothing's happening. Okay, so that's a 0. It's the same as being dropped on our suvat on the right. So any more numbers that we can put down? Yep, I haven't used the 78.4, the x. The x looks to me like the horizontal distance. So I'm going to put x in there. I am assuming now that this is the part of the journey I'm interested in, by the way, okay? So from here to here. And the next thing I need to do is deal with this 78.4. So there's two ways I can deal with this. I need to define my positive direction. So if I define down as being the positive direction, that's quite easy here because the particle never goes up, right? Nothing is up in this question. Everything is down. So if I define down as my positive for this one, I can set this to a positive 78.4 and I can set my acceleration to a positive 9.8 because they're working together in terms of S means something is below and acceleration wants things to go below. So they should be the same sign. So I can write it like that, or I could, if I was the other way around, I could make them both negatives. For now, let's just leave it like that. Anything else that I want to kind of work out here? Well, it says, if I read part A, it says the time taken to reach the surface. So the surface is when you are 78.4. So 78.4 is the right number to use with A. And the t value, I could call it a question mark or something like that. I'm just going to call it t. T is t. So we're now in our standard situation of 1, 2, 3, 4 bits of information means a suvac can be used. We're going to use S equals ut plus half at squared. And we're going to put all the numbers in. I'm just getting my notes. I've already worked these things out. So that means that we should end up writing 78.4 equals 0 times. So I'm going to just cross that bit out if you like. So 78.4 equals 1/2 times 9.8 times t squared. Okay, when you solve this, you should get that t is equal to 4. So t is equal to 4 describes when it's hitting the ground. Notice this is nothing to do. I haven't done anything at all with the horizontal. All I've done is I've found the time for it to hit the ground. Okay, so let's go back to the next question. So the next question is the horizontal distance travelled in that time. That time means that we can use the same value, and remember that this is a 4, okay? Distance equals speed times time, so 25 times 4, okay? So my answer to, let's go over here a little bit. So my answer to part B is going to be 4 times 25, which is 100 what? 100 meters. Okay, and finally, C, let's read C. The distance of the impact point from the original. So why is C a question? 100 can obviously not be the answer because we haven't done anything new. Distance means that what they're looking for here is they're actually looking for that value. Okay, distance means that we need to take into account both the horizontal and the vertical. So this is a right angle triangle, and we want to do 78.4 squared plus 100 squared, and we want the square root of that. And this ends up being approximately 130 meters. Okay, so that's kind of your first example there. Key ideas. Number 1, horizontally, no acceleration. I use distance, speed, time. Vertically, they're going to be suvat. You have to define your direction. In part A of the book, it will be relatively easy because everything's going the same way. Yeah, let's do another one. So this one here is the same question. Right, let's do this one here. So almost before I start answering, really, a habit of mine is I pretty much just start doing this straight away because it's so useful. So that's horizontal, that's vertical. In general, you should enter the speeds and the acceleration, or the initials. Okay, so what do I mean by that? So the speed here seems to be u, so I'm going to write u, and the reason for that is this s this S1 here, it will be U, right? It will be this for any journey in the question. The initial is always the same, right? That's why I'm also going to put a 0 there, because no matter which journey, it starts with 0. Everything's going down in the question, so let's define down as the positive, which means I'm now going to put in 9.8. Okay, and that's all I would actually do at the start, just those numbers there, because all the other values here depend on where the ball will travel to. If it's there, or if it's there, these are different journeys, so the numbers will be different, but these pretty much stay as it is, regardless of the journey, unless it's a very hard question. So let's read it now. A particle is projected horizontally with a speed of u from 1225.5 above. The particle hits the plane 90. Okay, let's start trying to put some numbers in this. So I'm talking about this part of the journey. So the distance at this point is 90. So I'll put a 90. Let's do that again. I'll put a 90 in there. I'll also put a 122.5 in there. Anything else I can do? That's about it, really, isn't it? What does the question say? Find the initial speed. So the initial speed here just means really what's u, okay? So I need some way of finding this out. So I don't have enough information over here at the moment to do anything with. On the right hand side though, I've got 1, 2, 3. So I can find something out, right? If you've got 3 bits of information, you can find out a 4th with SUVATs. So I'm going to think about this part of the journey because that goes with the 122.5. And I'm going to say that at this point, it has a value of t called t. Why am I doing this? I'm doing this because I can link these together. And then when I have this value, I can reuse that value, right? Because the same amount of time that it takes to get here vertically, it's the same t value as when it goes 90. So you often have this dynamic that you find out a t value from either the horizontal and use it in the vertical, or you use the vertical to help you with the horizontal. That's very, very common. So I'm going to try and make a SUVAT now for the one on the right. And let's have a look what I wrote down earlier. So again, we're going to use s equals ut plus half at squared, which is what we use a lot. We'll put some numbers in here. So we'll say 122.5 equals 0t. So I'm just going to cross that one out. Half a, so half 9.8 t squared. And if I do that, I should get a value of t that is 5 seconds if I solve that one. So that's useful because that moment in time is the same moment in time as I've got over here. So I'm going to use that 5. And you can now see I've got a 90, a u, and a 5. So distance equals speed times time. So 5u is equal to 90. U is equal to 18. So 18 meters per second. It says initial speed, so we should give units to it. So very, very similar to the first question. Again, write out your horizontal, write out your vertical, and this is often a special moment to use because the t value for these, you tend to sort of share that and find things out. It's going to be a good moment then for you to have a go now at this question. Try and put into effect the exact same steps. So pause the video for yourself first and have a go. And assuming you've now done that, we wanted to write this distance was 100, this was 20, so almost straight away really you could have worked out the t value was a 5 again. Now when we start substituting in here, so let's do the easy ones first. So that's a 0, that's a 9.8. What do they want in this question? Find h, right? H is an s value. Okay, and I know the time that goes with this, so I'm going to use that time again over here. Okay, so you wanted to use an s equals ut plus half at squared again, and that should have led to a calculation of half times 9.8 times 5 squared. The answer for that was 122.5 meters. Okay, I think that's a somewhat recycled question, isn't it, from the last one? Yeah, in fact, if you look, we already knew that. Or is that just a coincidence? I think that's just a coincidence, actually. Anyway, that's besides the point. So 122.5 meters is that number there. So vertical and horizontal are separate. Write your lists out. Write your speeds, your initial velocity, your accelerations down first. And then remember that the t value is shared between vertical and horizontal. That is the only thing really that is shared between the two.